Okay, today we'll discuss on uh, dislocations. This is the third lecture in the series on crystal imperfections. So this is basically the line defects, commonly known as dislocations. Now there are two types of line defects. One is the straight line defect, another one is the curved line defects. Again, straight line defects can be either edge dislocation or it can be screw dislocation. And both edge and screw are straight line defects, and curved line defects, that is the mixed dislocation. Okay, and remember, by line defect what we mean, that the defective region is along a line. So a small region, let us consider a curved line defect, and around this line if you consider a region which is in the order of say 2 to 3 atomic diameter, this is the region which is affected. Okay, so that is what is the line defect. So first we'll see the straight line defect, edge dislocation, then we'll see screw dislocation, and finally we'll see mixed dislocation. So first let us try to understand what is edge dislocation. So to understand this edge dislocation, let us assume that a set of vertical planes, as you can see here, some vertical planes has been shown. Here you can see this is one of the vertical plane. Here you can consider that this is a vertical plane. Okay, so in this way you can see there is another vertical plane. These are the different vertical planes there, and similarly you can see one midway there is a horizontal plane has been shown in blue color. So this is a horizontal plane that has been shown, and this vertical planes actually indicates that atoms are actually there in the crystal. So basically atoms are arranged in this way. Okay, and this is basically a virtual vertical plane that we are assuming actually atoms are there like this. Okay, so in this way atoms are there. Similarly, in all the planes you can consider the atoms are there. So instead of this atomic arrangement or the crystal structure, to make a good visualization, what we are doing, we are assuming these vertical planes, and always we will keep in our mind that actually atoms are arranged in these vertical planes, and we are looking these vertical planes or the horizontal planes as and when required. Okay, so first we'll try to understand that what is edge dislocation. Okay, see, this is the same picture that you have seen in the last slide. Here you see the first, the second vertical plane, this is the third vertical plane, this is the fourth vertical plane, fifth and sixth. So here you can see there are 6 vertical planes. Okay, and if you look carefully you can also see there is a horizontal plane also. There is a horizontal plane. You can see there is a horizontal plane. This is the horizontal plane. Sorry, this is the horizontal plane. Okay, and others are vertical planes, as you can see. Now actually atoms are there. I am just showing the atoms just above and below this particular blue plane. Let us consider atom is there, and they are bonded like this. Okay, similarly in the second layer maybe atoms are here and here, and they are bonded like this. In the third plane similarly atoms are like this and they are bonded. Fourth layer, atoms are there and they are bonded. The fifth layer, the atoms may be like this, they are bonded, and the sixth layer, similar fashion, you can think atoms are there, they are bonded like this. Now, I am not showing the other atoms. Definitely, there are atoms present along the vertical direction, along the horizontal in this direction also the atoms are there. I am not showing all these atoms. Just we are showing the atoms which are just above and below that particular plane. Exactly in a similar way, there are atoms which are just above and below the plane. If you go perpendicular to the slides, again, I am not drawing those atoms, but you have to visualize that all these atoms are actually there in the perpendicular to the plane also. So to make this picture clear, I am just removing all these atoms. I'm just removing, but remember all these are, this is basically a crystal structure, so all these atoms are present, okay? So this is what is the picture. Now we are doing a virtual experiment where we are basically along this plane A, B, C, D. Let us consider this plane is A, B, C, D. Let us consider the plane is A, B, C, D. And what we are doing, we are cutting this plane with the help of a very fine knife, which is practically not possible in the order of only angstrom level thickness. And we are actually cutting all the bonds which are there above and below this plane. So what we have done, the shaded portion only, not the whole plane, only the shaded portion we have cut with a knife. You just assume a virtual experiment we are doing, we cut all the bonds along this particular plane up to the shaded region, not the whole plane ABCD. We have cut only up to the region that I have shaded. Okay, so and let us consider that this is E and this is F. So A, B, F, E, this is the region that has been cut. That means all the bonds has been cut in this region. Okay, now what is done after cutting bonds, but remember this portion, the bonds are not cut. In the other region, the bonds are not cut. And what is done with respect to the bottom part? With respect to the bottom part, the top part is given a movement. The top part is given a force. So a force is given in the top part with respect to the bottom part. So bottom part is kept fixed. The bottom part is kept fixed. Okay, and the top part is given a force. So if this is done, then what will happen? If this is done, then what will happen? Just try to visualize that condition, that what will happen. So definitely it is expected that since this bond already cut, so this atom will now shift to the new position, maybe here I am showing by the yellow color. This atom will now come to this position, maybe at this location. This atom will go to this location maybe, and this atom it will go to this location. Okay, but and this atom will be there and it will try to make a bond with this atom, and this atom will try to make a bond with this atom. Okay, because they will now become close, and this will try to make a bond in this region, this will try to make a bond here. So now the new situation will be such, and this particular atom, if you look, that this atom will not get any atom to make bond because this bond is not cut at all. Okay, we have cut only up to this much. So this atom will not get any bond to which it can, will not get any atom to which it will make a bond. So this will be the situation. Now, if we want to look this particular situation, what will happen? You will see this kind of a picture. Just try to visualize what we have done. Here you can see perpendicular direction, other atoms also has been shown and their bonds has been shown. And when you cut and then if you give a push, then you will find that this set of atoms will try to make a bond with this one. This set of atom will try to make a bond with this one. But this set of atoms will not get any atoms with which they can make bond, because these bonds you actually not cut. So you will get this kind of a configuration. This part is clear or not? Can you visualize that what experiment we have done?
Yes, sir.
Okay. So this is the experiment, and through which you observe in the structure now a kind of defect. If you compare with respect to the perfect crystal structure, you know that it is a periodic regular arrangement. Everywhere it will be identical surrounding. If that is the perfect situation for a crystal structure, now if you look, if this kind of thing has happened, a region that is affected or some kind of imperfection or some kind of irregularity has come now in the crystal structure. And where is that region where this irregularity has come? If you observe carefully, the region is this one. This is the region where the irregularity actually come. This is the region. If you that actually it is a line. If you observe, these atoms are now closely spaced. If you compare with respect to the far away from this region, the distance or the periodicity between the atoms, you will observe that they are now closer. Okay, so these atoms are now under compression. If you compare with respect to the other regular atom, where the perfect part of the crystal, if you compare. On the other hand, just below this point, if you observe that this atom, distance between this atom is quite large in comparison with the regular distance in a perfect part of the crystal. So, and this thing will happen if you draw a line perpendicular to this region, right? So over around that region, basically, this is what is the defective region. So this is the region where you can see some kind of a compression energy, compression strain energy will be developed. Here you can see some kinds of tensile strain energy will be developed. So this is the imperfection. Now, so this particular imperfection, if you again go to the previous slide, and you can understand, this is the line actually around which, this is the line around which you observe the disturbance. So around this line, you will observe the disturbance. Just above it, you will find the compression. Just below it, you will find under tension, right? So EF is the line around which you are observing this imperfection. So this is a line imperfection, and this is a straight line imperfection. And what is that straight line? That straight line is FE, and this is called edge dislocation. So the edge dislocation, in this diagram, you can see the edge dislocation is what? Where is the edge dislocation? You can see this is the point. If you observe, and if you go perpendicular to the plane, then that line is basically, and here this is basically the F point that you can see from this end. Actually, if you go perpendicular in the other direction, then you will get the other side is probably E is there, because here it is the F, that point you can only see, and the other end it is basically the E, and around that line you will observe these defects. Above this line you will find under compression, and below that line you will find the atoms are under tension. So this is what is the edge dislocation. Okay, so now have you understood that what we mean by edge dislocation? It's a straight line defect. Which is the straight line that you have understood? What kind of defect, that also you have understood, I think. Now,
Sir, স্যার কম্প্রেশনকে একটু বুঝতে প্রবলেম হলো।
Compression means you can see that the atom distance between the atoms, these atoms, you can see they are much closer, na, if you compare with respect to the perfect part of the crystal. Because you see that what actually happened, they come closer, na, then what will happen, that there will be three atoms that we will observe, whereas in the perfect part maybe in this region and in this region, this is the distance. And here you can see that this distance is quite large if you compare with respect to the if you compare, if you observe here, you can see the regular part, that means the perfect part of the crystal. If you observe, this is the distance. If the distance between the atoms are closer, then what will happen? That will create a compression, na? If that is happen, that if the atoms are closer, then definitely the compression will take place, na? You are giving a push here. You
হ্যাঁ
have
স্যার।
not cut all these bonds. So then what will happen? The distance between this atom will be closer, na, if you compare with respect to the perfect part of the crystal,
Yes,
so
sir.
they will be under compression. On the other hand, if you see just below that region, you will find that they will be under tension, because the distance between them, you will find that quite larger with respect to the regular atomic distance. Okay, so this is what is meant by the compression and the tension in comparison to the perfect part of the crystal. Clear?
Yes, sir.
Okay, so this is what is the defect, and you have understood this is the line around which this defect is occurred, and this is called the edge dislocation. Why this is called edge dislocation? Because if you observe carefully, you see that these are the vertical planes now. You can observe these are the vertical planes now. A slight bend has been observed. You can see, but if you observe this particular plane, if you observe this particular plane, what is happening with this particular plane, which is, sorry, which is at this region. Oh, wait. So if you see this particular plane, you observe this is a particular plane actually. If you go in the other direction, this is basically the plane, you can understand, and along that plane basically the atoms are there, as you can see. Okay, so if you observe this particular plane, this plane is not a complete plane, this is a part plane, because other part is not there. There is no continuation of the plane, that means the atoms are missing, so that plane is not there. So this is a half plane, or a not a complete plane. Okay, so this is what is called the part plane. Okay, this is a part plane or incomplete plane, part plane or incomplete plane. Okay, so edge of the incomplete plane, so end of the incomplete plane, that is what is that line EF, the edge of that plane. That is why the name is edge dislocation, because that is the edge of this line. That means that particular line which is the edge of this plane. Okay, so this is what is the uh, edge dislocation. But remember, practically in crystal, edge dislocation is not created the way I have described you. I have just described you so that you can understand what is edge dislocation. It is not that someone is actually cutting with a knife and giving a push. It is a different during manufacturing processes, during different operations, these kind of edge dislocations are actually created. Okay, it is not that I'm just trying to visualize that what is edge dislocation. Okay, it is not the way that I have shown it is created in that way. Okay, so this is what is the edge dislocation. Now let us try to remember few important terminologies which are very important. So first thing is that the plane along which we actually cut this thing, or in other words the part plane is above that plane, this whole plane is called the slip plane. So this plane ABCD is called the slip plane. These are certain terminologies that you have to remember. So ABCD is called the slip plane. Okay, and here you can see what we did actually. We actually cut it up to this much, and this part is basically the slipped part, and this part is the unslipped part. So why slipped part? Because these bonds actually cut and this part actually moved forward or slipped over this plane. Okay, and this is the unslipped part. This is the unslipped part. Okay, so on the slip plane there are two parts. One is slipped part, another one is the unslipped part, and the junction of the slipped part and the unslipped part is basically what is the edge dislocation. So edge dislocation is basically the junction of the slipped part and unslipped part in the slip plane. Remember, this ABCD is the slip plane, because along this plane the slip of the crystal has occurred. Okay, you have given a push, it has moved, that is what is the slipped, and this is the region over which actually the atom slipped, and this is the region where you actually not cut the bond, that means the atoms not slipped. So that is the unslipped part, this is the slipped part, and this is the junction. Okay, these are the terminologies, very very important, and you have to remember. Next, few important points you see. Dislocation is a boundary between the slipped and unslipped parts of the crystal lying over the plane. We have already discussed this point. Okay. Next point is dislocation, direction, not dislocation, it should be direction. Direction and magnitude of slip is called the Burger vector of the dislocation. Okay, so we'll see that what is Burger vector. It is basically the magnitude of slip. We have just seen that one part of the crystal, here we have given the example that the upper part of the crystal is given a small push, and because of that the atoms moved by a small distance. So the distance by which it has actually moved is basically the amount of slip. So this magnitude of slip and the direction of slip is denoted by the Burger's vector. Okay, so Burger's vector is what? Burger's vector is generally given this symbol, and this indicates the magnitude and direction of the slip. That you have to remember. And we will see that how can we find out this Burger's vector. So to determine the Burger's vector, we draw a Burger's circuit. Okay, so by drawing a Burger circuit, we can find out the Burger's vector. So Burger circuit is a circuitous path passing through the perfect part of the crystal such that the net displacement along the path is 0. Okay, let us do it first and then we'll see. So let us consider this is a perfect crystal. Okay, let us consider this is a perfect crystal. There is no defects present, and we want to, this is 1, 2, 3, 4, 5, 6. Okay, and let us define the axis. Let us consider this is one direction of the axis, this is another direction of the axis, and this is another direction of the axis. Say this is A, this is B, and this is C. Let us consider these are the direction of the axis. Okay, now let us draw a circuit. Burger circuit means you have to start from any point. Let us consider we are starting from say this location. We are starting from this point. Okay, 1, 2, 3, 4, 5, 6. Okay, so now you see that suppose you start from here and move along this direction 2, 3, 4, 5. Suppose you have started from here and moving in this direction, come to this position. So how much you have moved? Along B direction, you have moved by plus 1, 2, 3, 4, 5. In the B direction, you have moved by plus 5. Then suppose there are different 1, 2, 3, 4, 5, 6. Let us consider there are atoms present at this interval. So in the C direction, how much you have moved? If you come here, you will move by a distance 1, 2, 3, 4, 5, 6. So along C direction, you have moved by minus 6 because C is the upward positive. Remember, we are going in this direction. Then along this direction, if you come, then along B direction, actually you have moved by minus 5. Okay, so along B direction, you have moved by minus 5. And similarly, if you go in this direction and come to the same location, so along C, basically you have moved by 6 direction and you come to the same location. So this particular circuit is what is called the Burgers circuit that you have drawn, and what you have found, the net displacement. What is the net displacement? You have found that the net displacement in the whole circuit is when the net displacement is 0, then you see that we reach to the same point where from we have started. That means this is a situation, since it is a perfect crystal, that is why we reach to the same location. Okay, now suppose this is a crystal, this is not a perfect crystal, and now you observe that what will happen if you draw the Burgers circuit. Okay, so let us again define the axis first. Let us consider the front direction. Let us consider this is the B. In the forward direction, suppose it is A, and the vertical direction is say C. Okay, let us start from this location. Suppose we are starting from here. Let us start from here. So first you go up to this point. So how much you have moved? Along B direction, you see 1, 2, 3, 4. So along B, you have moved plus 4. Next, you go down. So you are drawing the Burgers circuit around the defect, but remember, you always have to draw the Burgers circuit in a region where it is a perfect part, but around that defect. Okay, so this is the defective region here, you can see, and we are drawing the Burgers circuit a distance away, but such that it will enclose the defective region. So in the downward direction, that means the C direction, it has moved by 1, 2, 3, 4, 5. So in the C direction, it has moved by minus 5. Now you go in the in this direction. It is 1, 2, 3, 4. Okay. So in the B direction, now you go by minus 4. Okay. So then in the C direction, 1, 2, 3, 4, 5. In the C direction, you go to the plus 5. And you see, when you come to this location, your net displacement is 0. Your net displacement is equal to 0. So you come to a location where net displacement is 0, but still the circuit is not completed. So to complete the circuit, what is remaining? To complete the circuit, you have to draw one more line in this direction to complete the circuit, right? So this is what is the closure failure. This is what is the closure failure, because your Burgers circuit is not completed. So to complete the circuit, you have to draw a line in a particular direction, and definitely it will have certain magnitude. and that magnitude and direction is the Burgers vector. So this is what is the Burgers vector. So what you have to do to draw the to find the Burgers vector around the dislocation through the perfect part of the crystal, you have to draw a circuit, a circuitous path. Basically, you have to draw a circuitous path such that the net displacement is zero. And when the net displacement is zero, and if you find that if you are not coming to the initial position, then to join with the initial position, that particular vector is the Burgers vector in magnitude and direction. So is it clear that how to find out the Burgers vector through the Burgers circuit?
Yes, sir, clear.
Okay. So now you see,
স্যার একটা কোশ্চেন ছিল,
বলো।
আমরা যখন স্যার মানে ওই B+4 যেখানে ফার্স্টে করলেন, যেখান থেকে আমরা শুরু করেছিলাম,
ঠিক
ঠিক তার আগের পজিশন থেকে যদি আমরা শুরু করতাম তাহলে তো আমরা ওইখানেই পৌঁছে যেতাম।
না না, একদমই না। তুই করো না, কে বারণ করেছে তোমাকে? তুমি নিজে করো, তাহলে বুঝতে পারবে। করতাম না, অ্যাজ লং
একটা ডিজিট তো বেড়ে যেত স্যার তাহলে।
হ্যাঁ একদমই। তুমি ওটা এখানে তুমি 5 এ আসলে তোমার কখনোই হতো না, ঠিক আলটিমেটলি এই ঘটনাটাই ঘটতো যেটা হয়েছে। ঠিক আছে, সবসময় তাই আসবে, এটা আসতে বাধ্য। ঠিক আছে, তুমি করে দেখো, তুমি একই জায়গাতে আসবে। আমি এটা যাতে বোঝানোর সুবিধার জন্য এইভাবে করলাম। রাদার তুমি কোশ্চেনটা অন্য করতে পারতে। কোশ্চেনটা তুমি যদি এটা করতে যে স্যার আমি একটা কাজ করলাম, আমি এদিক থেকে না ঘুরে আমি ঠিক উল্টো দিকে ঘুরতাম, মানে আমি ধরুন এখান থেকে স্টার্ট করতাম। আমি যদি এখান থেকে স্টার্ট করতাম এবং আমি ক্লকওয়াইজ না গিয়ে যদি আমি অ্যান্টি ক্লকওয়াইজ যেতাম, তাহলে তো আমি এইখানে গিয়ে শেষ করতাম, তাই তো? So if we end at this location, in that case what will happen? In that case the direction of the Burgers vector will be opposite, is not it, to complete the circuit. So that is an ambiguity, that is true, but the point that you have raised is not correct. That you can definitely check, you will get the same Burgers vector in both magnitude and direction. That is not going to change. Okay, so now you see the points there, that Burgers circuit is a circuitous path passing through the perfect parts of the crystal such that the net displacement along the path is zero. Clear? Now Burgers vector is the closure failure of the Burgers circuit. Clear? There is a natural cause of ambiguity. What is the natural cause of ambiguity? That in which direction we should move, whether clockwise or anti-clockwise. If we consider clockwise, we are getting Burgers vector in a particular direction. If we consider anti-clockwise, we will get an opposite direction. So this will create an ambiguity that what is the actual direction of Burgers vector then. Clear? এত অবধি কি ক্লিয়ার আছে? এই তিনটে পয়েন্ট ক্লিয়ার হয়ে গেছে?
ইয়েস স্যার, ক্লিয়ার।
ওকে
স্যার একটা শুধু ওই স্লিপ এন্ড আনস্লিপ প্লেনটা ওইখানে ওই এটাতে একটা প্রবলেম আছে।
বলো।
এই যে প্লেনটাতে স্যার, এইখানে শুধুমাত্র এ বি ই এফ এইটুকু স্লিপ হবে, আর ই এফ ডি সি এটা হবে না, পুরোটাই তো একসঙ্গে হওয়ার কথা যদি এদিক থেকে একটা ফোর্স অ্যাপ্লাই হয়।
No, no, actually what we have done, we have actually cut the bonds above and below this portion. Okay, we cut all the bonds above and below this portion, but we did not cut the bonds in this region. These atoms, these bonds were not cut. The green bonds were not cut, but the yellow bonds are all cut along this shaded region. Okay, that is why when you are giving a push, then what will happen? Only the atoms which has been cut will move, but this bond will remain there, na? Only this bond will actually move, this atom will move with respect to this atom. Okay, then they will again create bonds with them, and that is a different issue, but they will actually shift with respect to the lower atoms because this bond actually cut, and that is why they are slipping over the slip plane. But these bonds actually not cut, that is why there is no question of slipping. Clear?
Yes sir, clear.
Okay. Now you see, to avoid the ambiguity was whether clockwise or anti-clockwise. This was the ambiguity. To avoid the ambiguity, we use right hand screw rule or right hand screw notation in drawing the Burgers circuit. That is very important. So that means we'll consider a particular direction of the dislocation line vector. So here our dislocation line vector is what? We have seen the dislocation line is FE. FE is the dislocation line. Okay, so now let us define a quantity which is called dislocation line vector, and given a symbol T, and this particular vector is basically, let us consider this is FE. So this EF is a line, but dislocation line vector not only having magnitude but also having direction. Question is that which one will be the direction of the dislocation line vector? That will be EF or FE. The answer is that is anything you can choose. Okay, so either you can choose FE or you can choose EF. That is up to you. There is no restriction. Okay, so first thing is that you select the dislocation line vector, direction of dislocation line vector, either FE or EFE. For example, we are considering FE. If we consider FE, so in that case, if you observe that particular picture, if you remember that slipped plane, this is F and this is E. Right? So what we are considering this is what is the T, dislocation line vector. So this is T, FE. So in the direction from F to E. Now what you do, use your right hand screw rule. Right hand screw rule is what? That you point your thumb towards the direction of dislocation line vector and rotate the Burger circuit in the direction of other four fingers indicates. Okay, so with your right hand, just point your thumb towards the direction of dislocation line vector and see that other four fingers is pointing in which direction, clockwise or anti-clockwise. So in this case, if we consider it is F to E, in that case, it is showing that the other four fingers, according to right hand screw rule, it will indicate this direction. That means clockwise. Right? That means a clockwise direction. So what we do, then we will draw the Burger circuit in the clockwise direction. So what is the rule now that we have set? This is the convention or a rule that we have set, that we will always follow right hand screw rule. First we select any one direction, either EF or FE. That is our choice. That is the dislocation line vector. Then we point our thumb towards that direction and other four fingers will indicate the rotation in which the Burger circuit is to be rotated. So this is the rule that we are going to follow. But again, the question may come to you that if the choice of direction T is arbitrary, then how that problem will be solved? Again, we can choose in the opposite direction and we can get the, in case of clockwise and anti-clockwise. But it is going to give you a consistent result. So consistency in what terms, that you have to understand very carefully. Now let us consider the situation that we have assumed T direction. Okay, then what we have done based on that T, that is F to E, that has been shown in this figure, we have to move the Burger circuit in the clockwise direction. So if we move the Burger circuit in the clockwise direction, at the end we have already seen we are going to get this as the Burger's vector, right? We are going to get this is the Burger's vector. That means you are going to get Burger's vector in this direction. You are going to get Burger's vector in this direction. Okay, so now you observe the quantity B cross T. What is this B cross T? The B cross T, what is the direction of B cross T? You see the B cross T, the direction is just perpendicular to the plane containing B and T, and that will be in the upward direction. Again, if you use the right hand screw rule, as you know that you point your four fingers moving from B to T, so thumb will give you the direction of B cross T. That means it is showing the upper part of the plane. So B cross T is showing the upper part of the plane. B cross T is showing upper part of the plane. This is clear. What is the direction of B cross T?
Yes, sir.
Okay. Now let us consider the reverse situation. Let us assume that T, we are assuming just the opposite direction. Let us consider T is not FE, but T we are assuming say EF. Okay, if we assume T is equal to EF, then let us draw the slip plane again. So this is now the T vector, clear? And if you do it, if you do the Burgers circuit, definitely Burgers circuit will be in the anti-clockwise direction. And if you do that, what you will get? Just the reverse direction of B you are going to get. Okay, so your B you will find will be just the reverse. So B is going to be in the reverse direction. Okay. This is going to be the B. Okay. So now you see that this is what is T and this is the direction of B. Now you see what is B cross T. See this B cross T. Now if you try to apply your right hand, the four fingers rotating from B to T, and you will again find that B cross T is indicating in the upper part of the plane. So in both the cases, whether you considering direction of T E to F or F to E, what finally you are going to get is that the consistent result of B cross T. And this B cross T actually indicates the direction of the part plane. That means if this is the slip plane, you observe the part plane is above the slip plane. So part plane is above the slip plane and this plane is actually missing. That means this is the location of this is actually the dislocation region. Okay, so this particular kind of edge dislocation is called positive dislocation, positive edge dislocation, and it is symbolized like this, as I have shown you, as if the slip plane and the part plane has been shown, and upper part will be the part plane. So you have seen that we are getting the consistent result even if we are considering the different direction of T. Okay, so individually the direction of T or the direction of B does not mean anything. Actually the consistent result means the position of the part plane with respect to the crystal, and that will define that whether it is a positive edge dislocation or a negative edge dislocation. Clear up to this much? How the ambiguity is resolved?
Yes, sir, clear.
Okay, so now you can see in this picture positive and negative edge dislocation has been shown here in this picture. Only the front view has been shown for the positive edge dislocation. You can see the picture that we have just seen, and here you can see the negative edge dislocation where you can see the part plane is at the bottom and the top part is actually no plane. So part plane is at the bottom. This is what is the negative edge dislocation. Okay, and always remember that in case of a edge dislocation, here you can see this is the region where the compression is there and this is the region where the tension force is there. So this is under principal strain energies are present, actually pure tension and pure compression that is present. Okay, in case of edge dislocation. So here you can see in case of a three-dimensional crystal, here you can see the position of the dislocation. You can observe this is the part plane. So edge of the part plane is basically the dislocation line. Okay. Now coming to the another straight line defect. Okay, edge dislocation is a straight line defect, and you have understood that EF was the straight line around which the defect was there. What kind of defect? You have seen that few atoms are very closely spaced, that is the compression, and lower the tension, the distance between the atoms were less. So this we have seen. Now screw dislocation is again a straight line defect. Okay, so exactly in a similar way, I try to give you a visual feel to understand that what is screw dislocation. See, again, these 6 vertical planes and that intermediate plane A, B, C, D. Now, what we are doing, as you know, the atoms were there above and below this plane. Like this. Similarly, atoms are there in that directions also. So I'm not showing all these atoms. You can understand that in this way it is there. Now what we are doing, now if we cut the plane, but we are not cutting like what we have done in case of edge dislocation, we are cutting this region now. And now we are cutting this region, and what we are doing is that with respect to the bottom part, keeping the bottom part fixed, we have given a small push to the upper part. Okay, we have given a small push to the upper part. So now try to visualize that what will happen. Now try to visualize. We have now cut in a different way. Remember, this part is the unslipped part. We have not cut it. We have cut only this, all the bonds above and below in this region. So along that plane, we have cut all the bonds only. And we have given a push at the top with respect to bottom. Now try to visualize that what will be the shape of the crystal because of that. See. So if you do that, definitely you will get this kind of a figure of the crystal. True? Can you visualize?
Yes, sir.
Okay. So this visualization is very important. And then only you'll be able to understand that where is the defect, which is the line, and what kind of defect it is. Okay. So if this is the condition now happen, now try to understand that where this defect will actually be there. So the defect, if you observe carefully, see these portions you have already cut, right? So this portion will simply slip, no problem. That will simply slip. But you just consider this region along that line. Let us consider this line is HG. Okay, this line HG. So along this line, you just observe that these atoms are moving with respect to the other atoms. Suppose here is one atom, here is another atom, and one atom is trying to move with respect to other atom, and it is kind of a shear. So that is quite clear from here. You can understand that one atom will move with respect to the other atom in this direction. So kind of a shear will be observed around that region. If you consider that line throughout, so around that region with respect to one another, there will be a shear that will affect. Okay, so kind of a shear force that will act. So it's a pure shear that will be observed under this situation. Previously, in case of edge dislocation, you have observed that it is a pure tensile and compression that will be there around that line. And here you can understand that there is a shearing force. You can understand that this is a kind of a shear. Na? If one part is moved with respect to the other part, this is what is the shear. And that shear effect will be definitely will be around that line, because this region will give some resistance, because this bonds actually not cut. So this part is trying to give the resistance, so that will try to defend the shear. So the shear stress will be developed in this region. Here all the bonds are cut, so this portion will not feel any shear. So where it will feel shear? When it will be resisted, right? It is the internal resistance which is basically the shear stress. Na? So the internal resistance will be come only when the bonds are connected. So around that line, around the line HG, around the line HG, basically the shear effect will come. So shear strain energy, shear stress will be developed around that region. So this is what is the line. Again, it is a straight line, and it is a screw edge. This is a screw dislocation. Okay, so this is a pure screw dislocation. Now again, we may be interested to find out what is the magnitude of the slip, what is the direction of the slip, and we know how can we measure this magnitude and direction by the Burgers vector. So we have to find out the Burgers vector in this case also. So let us try to find out the Burgers vector. The rule is exactly the same. So first you identify the dislocation line vector. So dislocation line vector, either you consider H to G or G to H, that is your choice. Let us consider HG is our dislocation line vector. Let us consider the dislocation line vector is H to G. Okay, here you can see this point is basically H, and G is on the other hand maybe here. Okay, HG. Let us consider HG is the dislocation line vector. So if HG is the dislocation line vector, then which direction Burger circuit is to be drawn, clockwise or anti-clockwise? Anyone? In which direction we should draw Burger circuit, clockwise or anti-clockwise? HG, you see HG. So in which direction we'll draw Burger circuit? Here it is H, here it is G. So H to G means this. So we have to draw the Burger circuit in a clockwise direction. Very good. So in a clockwise direction, we have to draw the Burger circuit. So let us start drawing the Burger circuit. Remember, we have to draw the Burger circuit in the perfect part of the crystal, but around that region of defect. So we know the region of defect is HG, but around it, in the perfect part of the crystal, we have to draw the Burger circuit. So let us start drawing Burger circuit from the point D. So first, in the clockwise direction, let us move to this location. Before that, let us consider the directions. Say this is one direction, this is another direction, and this is another direction. Okay, say this is A, this is B, and this is C. This is the axis. Okay, so from D to we come to this position, means 1, 2, 3, 4, 5, 6. So in the C direction, we have moved by plus 6. Then from here to here, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the A direction, we have moved, we have moved minus 12. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the C direction, we have moved minus 12. Sorry, C already given, so minus 12. Okay. Then from here to in the A direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So in the A direction, we have moved plus 12. Okay. Now in the plus C direction, 1, 2, 3, 4, 5, 6. So plus 6 in the C direction. So burger net displacement is 0. Okay. So if the net displacement is 0, then it is clear the closure failure is this one. So this is what is the Burgers vector B. So this is the closure failure. So this is the closure failure. So this is what is the Burgers vector. So in this way we can find out the Burger vector. Okay. And what you have observed is that previously in case of edge dislocation, if you observed carefully, you will find that B and T, they are perpendicular to each other. In case of edge dislocation, you have seen that B and T are perpendicular. T means dislocation line vector, and Burgers vector, they were perpendicular. If you remember, that was T, that was B, like that. Okay, so they were perpendicular. But in case of a screw dislocation, you observe that we have considered T from H to G. That means this was the direction of T, and finally we have observed that the direction of B is this one. So what we have observed is that T and B are 180-degree apart in this particular example. So B and T are basically along the same line. In this particular example, they are opposite in sense and they are 180-degree apart. So this particular screw is called a negative screw. This is a negative screw. Okay. So one important observation is that in case of a screw dislocation, B and T are in the along the same line, maybe in the same direction or in the opposite direction. If they are in the same direction, it is a positive screw. If they are in the opposite direction, then it is a negative screw. Okay. And so positive and negative screw, I have just mentioned that if B and T, if they are in the same direction, that is a positive screw, and if B and T are in opposite direction, then that is a negative screw. Okay. Now we'll see the curved line, a curved dislocation, curved line defect or the curved dislocation, and that is called the mixed dislocation. Okay, so we'll start from the same figure so that we can visualize this kind of thing. So 1, 2, 3, 4, 5, 6, and the same plane, that slip plane. And what now we are going to cut is that we are going to cut a region which is this one. Okay, now we are going to cut a region like this, and the top portion we are going to give a push with respect to the bottom portion, and then try to visualize that what will happen to the crystal. Okay, so in that case you will find the picture as you can see here. You see that this is now the line around which you will find the defect. If you consider exactly point A, you will find a pure screw dislocation. If you consider this point B, you will find a pure edge dislocation. But in between the other points, you will find that it is a mixed kind of a dislocation. So basically, the line around which the defect will occur is this line. So this is basically the curved line. Okay, that is going to, so this is say H and this is say F. So this is the line around which the defect will occur, and exactly at H. So what is the dislocation line vector now? Remember, dislocation line vector will be tangent to this line. Okay, dislocation line vector will be tangent to this line. Previously, it was very simple, along EF or along GH. That was the dislocation line vector because they were straight line. But now it is a curved line. So dislocation line vector will be tangent. So at point H, maybe this is the dislocation line vector T. At this point location, maybe the tangent. This is the dislocation line vector. So these are the direction of dislocation line vector. At point F, this is the tangent. So this is the dislocation line vector. Okay, so it is the tangent. So this is what is the basic idea, that how we consider the dislocation line vector in case of mixed dislocation or a curved line, that you have understood. And to find out the Burgers vector, exactly the similar method. And most interestingly, if you do this exercise of finding out the Burger vector,
If
yes, yes,
বলছি স্যার এফ পয়েন্টে কি ট্যানজেন্টটা নিচের দিকে আছে?
কোনটা?
ওই যে এফ পয়েন্টে যে ট্যানজেন্টটা এঁকেছে ওটা কি নিচের দিকে?
না না না, এটা একটু আমি 3 ডাইমেনশনাল আঁকতে গিয়ে একটু গন্ডগোল করেছি এটা।
আচ্ছা বুঝতে নিচের দিকে নয় তো?
না না না, ওরকম কিছু নয়। ডেফিনেটলি ওটা ওই প্লেনেই থাকবে, ডেফিনেটলি ইট ইজ ইন দ্যাট প্লেন, নো ডাউট অ্যাবাউট
আচ্ছা
দ্যাট।
বুঝতে পেরেছি।
বুঝতে পেরেছে তো? এটা ডেফিনেটলি ইন দ্যাট প্লেন। ওকে, so now you can understand that in case of a mixed dislocation, how we can also say exactly in a similar method we can find out the Burgers vector. The question is that what interestingly you are going to observe is that if we follow, let us consider, if we assume the direction is T in that direction, okay, then you will find the Burgers vector will come exactly what we have got earlier. That means this one. And again, around this edge dislocation, if you draw this Burgers circuit and find out the Burgers vector, you will observe that your Burger vector is coming exactly in the same direction. So it is immaterial that whether it is a edge is there, screw is there, or both components, edge and screw, are present. Remember that throughout the crystal, the Burgers vector is same. That is a very interesting observation that you will find if you just do this exercise of your own. You can find out the Burger vector considering this. Around this point you draw the circuit, around this point you draw the circuit, and both cases you are going to get the same Burger vector, same direction, same magnitude. That means that even if the situation is a curved one, Burgers vector everywhere is going to be same, and that Burgers vector in this particular example is going to be this one. Maybe it is in this direction. So everywhere you will find that the Burgers vector will be same. Okay, so it is same here. Burgers vector everywhere will be same, B. So here you can see at this region, you see that this B and this T, they are 90-degree apart at this location. Here at this location you see that T and B are exactly opposite to each other. That means this point is a pure screw, whereas it is 90-degree. That means this point is a pure edge. Now depending upon their direction, B and T, you can also identify whether it is a positive edge or a negative edge. Similarly, considering this B and T, you can also find out whether it is a negative screw or a positive screw. And in other locations where it is, you see that B and T are making some angle, maybe say T is like this, maybe T is like this, and B is like this. So in that case, definitely you can understand there are two components. One is screw and another one is edge, because that particular T you can divide into two components, one component in this direction, another component in this direction, and this component will produce edge component, and this component is going to produce a screw component. So in other locations, basically it is a general state of stress that will be there. Both tensile compression along with the shear will be there. But at the screw only shear strain around that point will be there. In case of pure edge, only pure tensile and compression will be there around that point. In the other locations where it is both components are present, okay, when that means the T and B will make some angle, not 180 or 90 or 270. So in that case, definitely it's a general state of stress. That means both tension compression as well as the shear will be present. Exactly as you know, in case of a Mohr circle, you know that in case of principal stresses only the normal stresses are present. There is no shear. That is the case for the edge dislocation. Similarly, the pure shear, that is the case of screw dislocation. In other points of the Mohr circle, you know that is a general state of stress where both normal stress and the shear stress are present. Exactly the same picture is here also. Within the crystal, the strain field is distributed in that way along the around the line. Okay, any confusion?
No, sir.
Okay. So this picture, I think, is much more clear about the same thing. To give a better visualization, I have also taken this picture. Here you can see the pure edge you will observe at this location, pure screw and intermediate. It is going to. This is what is the mixed dislocation line. This general curve is a mixed dislocation. It's a curved line around the defects. Okay. So again, if we recapitulate that whatever we have done till now, that dislocations are not in thermodynamic equilibrium. That is a very, very important. We have seen in the last class that some of the point defects are in thermodynamically stable equilibrium, and we have also calculated that what fraction will be in stable equilibrium. If they are in stable equilibrium, obviously they will be present within the material, though they are defect, but they are in equilibrium, so they will be present within the material. But remember, dislocations are not in thermodynamic equilibrium. Since dislocations are not in thermodynamic equilibrium, there is always a tendency for them to leave the crystal. Okay, whenever they get a chance, wherever they get a chance, they are trying to get out of the crystal. Okay, because they are not in a thermodynamically stable equilibrium within the material. That is the first difference if you compare with respect to the point defects, that you have to remember. But still, a lot of dislocations are always present within the material. It is not that dislocations simply go out of the crystal if you heat it up. Okay, even after a good amount of annealing, you will find that still there will be a lot of dislocations are present. Okay, we'll see that what is the effect of dislocation and all that with the material property. But let us first try to understand what is dislocation clearly. Then dislocation is a boundary between the slipped and the unslipped part of the crystal lying over the slip plane that we have understood. Burger's vector gives the direction and magnitude of the slip and is an important characteristic of the dislocation. Okay, to determine the Burger's vector, we draw a Burger's circuit around the dislocation and use RHS notation for it. Okay, Burger's vector is the closure failure of the Burger circuit. I think all these points are clear to everyone.
Yes, sir. Clear.
Now, the stress field in dislocation, as I have already told you, that in case of edge dislocation, the stress field is the principal stress field. That means here you can see it will be under compression, and this is the region. This is the region where it will be under tension. It is actually negative edge dislocation that has been shown. Here you can see this is the part plane and this is the slip plane. Okay, so this is the negative edge dislocation has been shown. So this is under tension and this is the region which is under compression. You can see the distance between the atoms are closer if you compare with respect to the regular atomic distance, and here it is larger if you compare it with other. So this will be in compression. So principal strain field will be there, and if you compare consider in case of a pure screw, you know that it will be a shear, pure shear will be there. But if it is a mixed dislocation, in that case you know that the general state of strain or the stress field will be there around that line.